Hello everyone, my name is Chinta Teja. Currently, I am pursuing BTech second year in Information Technology from Institute of Aeronautical Engineering. Today, I am here to give a presentation regarding the complex engineering problem of the subject Design Analysis and Algorithm. So, the title of the complex engineering problem is Optimal BST. So, I'll continue with my presentation about the problem. An optimal binary search tree is a type of binary search tree that is designed to minimize the expected cost of searching for elements. In a standard binary search tree, the structure of the tree depends on the order in which keys are inserted, which may lead to inefficient search times if the tree becomes unbalanced. However, an OBST is constructed by considering the frequency or probability of access for each key, ensuring that the frequently searched elements are placed closer to the root of the tree. This reduces the average number of comparisons required during search operations and improves overall efficiency. The concept of an OBST is particularly useful in applications where search operations are performed repeatedly, such as in compilers, database systems, and dictionaries. In such scenarios, certain keys are accessed more frequently than others, and organizing the tree based on these access patterns leads to significant performance gains. The goal is to minimize the weighted path length of the tree, where each node's depth is multiplied by its probability of being accessed. By doing so, the tree ensures that commonly accessed nodes require fewer comparisons. Construction. To construct an OBST, dynamic programming is typically used. The algorithm takes as an input a sorted list of keys along with their probabilities of successful searches as well as probabilities of unsuccessful searches between keys. It then systematically evaluates all possible subtrees and calculates the expected cost for each configuration. The cost is computed by summing the probabilities of all nodes in a subtree and adding it to the cost of its left and right subtrees. By storing intermediate results in a table, the algorithm avoids redundant calculations and efficiently determines the optimal structure. The process begins by initializing cost and weight matrices, which store the cumulative probabilities and minimum costs for different subtrees. The algorithm then considers trees of increasing sizes, starting from single node trees and gradually building up to the full tree. For each subtree, it tries every possible key as the root and calculates the resulting cost. The route that yields the minimum cost is selected, and the process continues until the optimal tree for all keys is constructed. Although this approach ensures optimality, it has time complexity of big O of n cubed in its basic form, which can be reduced to big O of n squared with certain optimizations. Construction. Despite its advantages, constructing an OBST can be computationally intensive, especially for large data sets. However, once the tree is built, the search operations become highly efficient, making it ideal for static data sets where the set of keys and their access probabilities do not change frequently. In dynamic environments where insertions and deletions occur often, maintaining an OBST becomes more challenging. Nevertheless, the concept remains fundamental in understanding how data structures can be optimized based on usage patterns. Introduction. Searching is a basic operation in computing. BST efficiency depends on structure. Unbalanced trees increase search time. Balanced trees are not always optimal. Optimal BST uses access frequency, improves average search performance, used in databases and compilers, helps in faster data retrieval, focuses on minimizing search cost. Objectives. Understand binary search trees. Learn optimal BST concept. Study cost optimization techniques. Implement algorithm using DP. Compare naive and DP methods. Dynamic programming. Analyze time complexity. Analyze space complexity. Improve search efficiency. Apply in real world scenarios. You can see the given optimal binary search tree, which exactly looks like a binary search tree with root node and its children. Prerequisites: basic knowledge of BST operations, understanding of recursion, knowledge of dynamic programming, familiarity with time complexity, basic Java programming skills, understanding arrays and matrices, problem solving skills, algorithm design basics, logical thinking ability. Problem statement: given sorted keys and frequencies, each key has search importance. Construct BST with minimum cost. Cost depends on node depth. Frequently used keys near root. Reduce total weighted search cost. Maintain BST properties. Find optimal tree structure. Ensure efficient searching. As you can see, there's given two examples where one is a balanced BST and another one is optimal BST, where an balanced BST gives an output of 1.3, whereas the optimal BST gives the shortest path of 1 point. Cost formula. Cost is equal to sigma of frequency into level. A root node has level 1. Deeper nodes increase cost. Frequency determines node position. Higher frequency near root. Lower frequency placed deeper. Total cost is sum of all nodes. Used to evaluate BST efficiency. Goal is to minimize total cost. Naive approach. Generate all possible BSTs. Compute cost for each tree. Compare all configurations. Select minimum cost tree. Large number of possibilities. Time complexity is exponential. Not suitable for large inputs. Very slow and inefficient. High computation overhead. Dynamic programming approach. Divide problem into subproblems. Store intermediate results. Use bottom up approach. Avoid recomputation. Use cost table for storage. Efficient compared to naive method. Time complexity of big O of n cube. Page complexity of big O of n square. Suitable for moderate inputs. Algorithm steps. Initialize cost matrix. Fill diagonal with frequencies. Increase chain length by step. Compute sum of frequencies. Try all possible routes. Calculate cost for each route. Choose minimum cost. Store result in matrix. Return final optimal cost. Code implementation. Use 2D array for cost storage. Initialize base cases. Use nested loops for computation. Function to calculate frequency sum. Compare and update minimum cost. Store results in matrix. Return optimal cost value. Implemented in Java language. Ensures efficient computation. Performance comparison. Naive approach is very slow. DP approach is much faster. Reduces redundant calculations. Uses extra memory for speed. Time complexity significantly reduced. Improves efficiency drastically. Suitable for practical applications. Demonstrates optimization technique. Better scalability than naive method. Results and observations. High frequency keys near root. Low frequency keys deeper in root in tree. Cost significantly reduced. Dynamic programming avoids repeated calculations. Efficient tree structure formed. Works well for moderate inputs. Improves search performance. Validates algorithm effectiveness. Confirms theoretical expectations. Conclusion: optimal BST improves search efficiency, uses frequency-based optimization. Dynamic programming provides solution, reduces time complexity, better than naive approach, useful in many applications, demonstrates algorithm optimization, enhances data retrieval speed, important concept in data structures. In conclusion, an optimal binary search tree is a powerful technique for improving search efficiency by leveraging access probabilities by carefully arranging nodes to minimize expected search cost. It provides a more efficient alternative to traditional binary search trees in scenarios where access patterns are known in advance. Future scope: improve using NUT optimization, reduce time complexity to big O of n square, handle unsuccessful search cases, apply in database indexing, use parallel processing, extend to large data sets, optimize memory usage, implement real time systems, explore advanced optimization techniques. Thank you for the opportunity.